Okay.
All right. Hello, everybody, and welcome back for the last day of the summer school. It has been a very exciting, fun, but very exhausting week, I must say. I'm happy to be back to try and wrap up the discussion that we've been having about QCD, the non-abelian nature of QCD, where it comes from, how it works, and then ultimately today trying to bring it around to how does that lead inevitably to gluon saturation and why should you care? I have to say I am not as prepared for this evening as I really wanted to be. I got stuck behind departmental duties during the day. So I have various fragments of notes that I want to share to you, but I wanted this all to be a little bit more structured and organized. So I apologize if I'm a little incoherent and bouncing around. I didn't get to tie everything together to quite the level that I wanted to today. Still, nevertheless, I think we can wrap up the core message, and you'll see the point of this whole discussion. So last time we were talking about scattering of quarks at high energies in QCD. This is scattering in the Eichenal limit. This was also referred to as Reggie kinematics. The forward scattering limit where mandelstam S is going to infinity, but the transverse momentum exchange T is held fixed, so that overwhelmingly particles scatter in the forward direction. This is associated with small Bjorken X in deep inelastic scattering. We did a couple of calculations last time. We did the elastic scattering cross-section, quark-quark goes to quark-quark, mediated by either T or U channel gluon exchange. Although in the Eichenal limit, the U channel process was irrelevant, and we only needed the T channel process. This is, let's say, the lowest order contribution to the inclusive final state, where I could be looking for quark-quark goes to anything, in which case quark-quark is just the lowest contribution to the inclusive X final state. The next thing that I can create next to leading order is one additional particle, namely the emission of gluon. So we took the diagram, the one T channel diagram that gave us quark-quark scattering, and we dressed it up with radiation of the soft gluon in all possible ways. There were 5 potential diagrams, and we spent a significant amount of time calculating these 2 particular diagrams. I called them diagram A and diagram B. Diagram A is a final state radiation diagram where the radiation is coming off of this quark line, which I might call the projectile. This particular particle is moving with a large P- momentum. This is the radiation off of the same particle, but initial state. And what we showed is that these 2 diagrams in Eichenal kinematics are identical up to a minus sign. And that minus sign is entirely attributable to whether this intermediate state is moving into the future, something time-like, or something which is moving in a space-like direction, so there's negative virtuality. Kinematically, otherwise, they're identical. So that if you are in an abelian theory, then what this predicts is a perfect cancellation of the intensity pattern of radiated photons coming from initial versus final state radiation. But in a non-abelian theory like QCD, precisely that non-abelian nature shows up because instead of getting 0, you get a difference of color matrices in 2 different orders that gives you a commutator. So the high energy limit is exquisitely sensitive to non-abelian physics in a way that it just isn't. It's not interesting, or it's not that exciting. There's not that much going on for an abelian. One thing that I didn't emphasize last time is our convenient flexibility to suppress certain diagrams depending on our choice of gauge. We focused particularly on this radiation from the P- going projectile. And what we found when we added these diagrams together was that commutator gave us something proportional to the structure constants FABC, but also notice the particular part of the final state gluon polarization that shows up here. This picks out a particular component, epsilon plus. And that means that if I chose to work in a gauge such that epsilon plus is equal to 0, namely the light cone gauge A plus equal to 0, in this gauge, actually these diagrams would go away. We were doing this calculation in Feynman gauge, so that's a symmetric gauge where all 5 of the diagrams all have a non-trivial contribution and you have to add them all up. But if you strategically choose an asymmetric gauge, then you can eliminate, in this case, all radiation from the P minus going projectile. And the essential reason is that the vertex that comes in here to radiate that final state gluon has epsilon plus together with P minus. I pick up the largest momentum in that forward going quark line, which is that P1 minus, and that wants to pair up with epsilon plus. So I can choose epsilon plus equals 0 to suppress radiation from the P minus going particle, or I could choose the A minus equals 0 gauge that will suppress radiation. So we will take advantage of that choice to strategically put all of the dynamics in one half of this process in a few minutes, and then sort of reduce the target to a passive scattering operator. And we'll explicitly calculate the radiation coming off of the projectile. So that's just a comment about this. Let's see, what other comments to make before I move on? One thing that I wanted to mention but didn't see a good place to put it before now, I guess, is this process is talking about elastic quark-quark scattering as if I could take an on-shell quark from minus infinity to plus infinity exactly the same way that I would with an electron or a scalar particle or anything else. So this is sort of a picture where I can realistically have a quark coming from time minus infinity, another quark coming in at time minus infinity, and then they collide and they go back out. As if I could have a beam of quarks at the LHC. This is, of course, an absolute lie. There is no such thing as an on-shell beam of quarks from the LHC or anything else. What we have is hadrons. So it's a useful theoretical exercise to calculate the quark-quark scattering, but this is never the whole story. It always takes place as a part of a whole hadron cross-section. And the closest analog that you get to that is as a part of a factorization theorem. So if you're looking for, let's say, semi-inclusive deep and elastic scattering, where I have an electron that comes in, a proton, the electron exchanges a virtual photon with the target, and then the proton provides a quark that gets hit by the virtual photon. That outgoing quark then fragments into whatever final state, including maybe a particular tag habit, say an ion. This particular process is built out of several ingredients. There's a non-perturbative distribution function called a parton distribution function. Really, the PDF is like the amplitude squared version, so it has both the annihilation operator and the creation operator that puts it back. But there's a non-perturbative distribution in the initial state. Potentially, there's also a fragmentation function describing the non-perturbative transition from a single quark to a jet of on-shell hadrons, including some particular one that you measure. But right here in the middle of the process is the hard scattering part. This is the part where the high virtuality Q squared from the photon causes a short distance interaction. This is as close as we ever really get, this kind of hard scattering kernel as a part of a bigger process. That's about as close as we ever get to individual parton-parton scattering. So there is a sense in which this is true, that you actually have quark-quark scattering, but it's never as a literal like LSZ implementation of a particle coming from minus infinity and scattering to the asymptotic future at plus infinity. It's effectively something like that on timescales that are well separated compared to the hadron dynamics. So just a comment, we calculate this as if it's quark-quark scattering, which is of course a fiction, but it's still useful nonetheless. Okay, so at the end of the calculation yesterday, we arrived at the cross-section. So that NLO cross-section for the gluon emission was d sigma d2 kpert dy d2 qpert equals 2 alpha s cubed cf over pi squared 1 over q perp squared, 1 over k perp squared, 1 over k plus q perp squared. Where q was the momentum transfer between the incoming and outgoing quark. So this momentum transfer is q, and k was the momentum of the radiated. Here y is the rapidity of the radiated gluon. So this is y equals 1/2 log k plus over k minus. So the important features that we constructed from this were that first off, the scattering process is unsuppressed at high energies. It is not power suppressed as S goes to infinity, just like the leading order one has. Second comment is there's certain transverse momentum dependence here, but this is reflective of the specifics of single quark scattering on single quark. The transverse momentum distribution would change if there's internal structure to these instead of them just being point-like particles. So if I have instead of quark-quark scattering, maybe I have QQ bar dipole scattering. Then I'll have a similar expression for the gluon radiation, but the transverse profile will change. It'll have something that's sensitive to the typical sizes and scales of the projectile. So you can expect that if I generalize from quark-quark scattering to eventually, say, proton-proton scattering, the transverse momentum distribution will change and be interesting and maybe not perturbing. But the thing that's really interesting about it is that this is a boost invariant distribution. It's independent of the rapidity. So if I integrate out all the rest of that stuff, I just get some number. But the important part for me is that distribution per unit rapidity is constant. And that means even though compared to the elastic cross-section, right, this amplitude squared was a process that happened at order alpha s squared. This correction is something that goes like order alpha s cubed. So in principle, this is an improbable correction, something that happens rarely at weak coupling. But even though this process is down by a factor of alpha s, which is much less than 1 by assumption, it actually can happen at low probability over a very large phase space. So if I take that d sigma dy equals constant, then I integrate it over the entire distribution, the entire phase space. What I end up getting is a large log. So for purposes of comparison, let me take the distribution here at NLO and divide it by the elastic scattering cross section. So I get the ratio is some measure of the extra suppression that I have to radiated gluon versus not. So if I look at, let's say, the sigma dy for my NLO process, and then I divide it by, let's say, my elastic scattering cross section integrated. This is some measure of a multiplicity. So it's similar to a number distribution that I'm pulling out of this ratio. So when I compare these things, so if this is what I take from the leading order cross section, and this is something that happens at next to leading order, this ratio is down by a power of alpha s. The constants will work themselves out. But then when I compare that, the total probability, right? If I integrate this thing over the rapidity window, I integrate alpha s times dy over the entire window of the collision, that means I integrate from my maximum negative rapidity to my maximum positive rapidity. So this is my light cone plus direction, my light cone minus direction. Y equals 0 is here, y equals plus infinity would be moving at the speed of light along the plus z-axis. Y equals minus infinity would be moving along the speed of light at the negative z-axis. For purposes of evaluating this integral, I can't just do minus to plus infinity. That would be nonsense. I have a large phase space, but it's not literally infinite. So if I put my precise kinematics back in, so if I have a massive particle, something that is not necessarily light-like, I've got, let's say, P1 mu going along the plus direction, P2 mu going along the minus direction. Actually, I think it was the other way. P1 was going along minus P2 was going along. So if P1 mu is, let's see, a large P1 minus, by definition, nothing along the perp direction. And if I include a finite mass, then it has non-zero plus component. It would be m squared over 2P1 minus. Likewise, P2 mu has a large plus component. It has a small on-shell minus component, but by construction, zero transverse momentum. The range of rapidity that I can integrate over is over the entire rapidity interval of the collision. So I can go up to y max. That is the rapidity of, I guess, particle number 2. So that is rapidity of P2. And my minimum rapidity is the one coming from particle number 1. So if I calculate that ratio, and I look at this quark to quark glue divided by quark goes to quark, we get alpha s, and then the difference in rapidity y2 minus y1. So that's alpha s over 2 log P2 plus over P2 minus log P1 plus over P1 minus, and then I combine the logs together. So I get log P2 plus P1 minus over the small components P1 plus P2 minus. I can put a factor of 2 in both places if I want. 2P2 plus P1 minus is Mandelstam S. So this is log S, and then from the on-shell conditions down here, my P1 plus is m squared over 2 P1 minus, my P2 minus is m squared over 2 P2 plus. I clean things up down here. I have another factor of 2, and then I have m to the 4th. This is 2 plus P1 minus, which is another factor of s. So I get log of s squared over m to the 4th. And then I can pull out a factor of 2 that cancels this one, and I get alpha s log s over m squared. There we go. So the point is that if I ask, what is the probability that I radiate a gluon, a soft gluon, in addition to this high energy scattering, the probability that I radiate the gluon in a particular rapidity slice is small. But the fact that I have high energy scattering means that I have a logarithmically large amount of rapidity in which to radiate. So it's really like saying, if I look at my particle production, dm dy, as a function of y, I expect to see constant as a function of y, as long as my approximations hold. My approximations will start to break down somewhere over here when I get close to beam rapidity y2, and somewhere down here when I get close to the other beam rapidity y1. But in the middle, I expect it to be a constant distribution, and this is a very large phase space. So the idea is that even though the value here is parametrically small, something proportional to alpha s, the area underneath that rectangle, that pedestal, leads to a high probability overall, high expected number of gluons that get radiated. So this is what's being described here, is that you have a competition between low probability, alpha s much less than 1, with a large phase space. In this case, that is y total, which is log s over m squared, is much greater. And of course, this is the basis of our logarithmic resummation. If the phase space eventually gets large enough such that this is no longer a small number, alpha s log s over m squared is order 1 instead of being much less than 1. Once I hit this threshold, I need to do a resummation. What does that mean? It means that if I have a huge amount of phase space in which to radiate soft gluons, then not only do I conclude that compared to 0 gluons, one extra gluon I can get for free because this is a factor of alpha S log S over n squared, and that's order 1. Well, if one of them is order 1, then 2 of them are also order 1. Because that's alpha S log S over n squared whole squared, and so on and so forth. So what this tells us is that actually in this limit, when I have a really large amount of phase space, I expect to get a massive amount of gluon radiation. I have not just one gluon, but a whole cascade of gluons. And so my picture is that as I go to higher and higher S, or lower and lower Bjorken X, that I induce more and more radiation because I have higher and higher phase space in which to fill those radiated gluons. So the key physics is that QCD produces a boost invariant spectrum of gluon radiation. That is a generic consequence of it being non-abelian, vector bosons, and the Eikenel limit. If you have those three things, pretty much everything else follows automatically. The sketch that I drew here of the rapidity distribution is in principle for gluons, but I think it's remarkable to compare that with actual experimental data from the LHC. This is a plot of measured particle production. I think this was inclusive charged hadrons at CMS in proton-proton collisions at 13 TeV. One thing to note is that the horizontal axis here is not the momentum space rapidity, it is the pseudo rapidity. So there's a non-trivial change of variables associated with that distorts the shape a little bit. But I think the point is quite clear that to a remarkable approximation of over 5 units of rapidity, the whole acceptance of the barrel detector, you have a largely constant distribution of hadrons. And in principle, that pedestal should extend almost all the way up to plus and minus beam rapidity, which is something like 5 units here, if I recall correctly. So we see this to actually be true in real life, that QCD produces a boost invariant distribution of hadrons at mid rapidity to excellent approximation. And the logical conclusion of that is if this continues to happen, then at high enough energies, I expect to reach a region of extremely high gluon densities, where I don't have dilute scattering anymore, even though I'm working in perturbation theory and short distances. I can have a very high density of gluons that's going to change the nature of my perturbation series. So the picture that starts to emerge of high energy scattering.
I just have a question.
Yes, please.
So the thing that you've shown is in this limit, the production of gluons is pretty much equal throughout all of rapidity. But I guess my question is, how does the fact that we're now adding, as you get to higher energies, these new terms, the next and next and next, the leading order terms, are equally probable? I don't fully understand.
Yes, okay, so good question. Really what I should say is that they're not automatically going to generate these logs. I have to ensure that the kinematics are nested in such a way that at every step I continue to generate that large phase space. So good point. If I want to have multiple gluon emissions of this type, we basically show that I get that constant distribution of gluons anytime, let's say I have that large P minus up here and a large P plus down here. In order to get that log, my K, let's say K number 1 that comes out, its minus momentum has to be very small compared to the one that came before it, such that subtracting this minus momentum does not alter the Eikenel trajectory of this particle at all. Likewise, I need the plus momentum to be much smaller than this one. So this was minus 52. So now if I have a second gluon emission, this one needs to be ordered with respect to the one that came before it. So now this, if this first gluon needed to be solved compared to the projectile, in order for this one to also get a boost invariant distribution, it needs to be solved compared to everything that came before it. So this one needs to be solved compared to K1, which is itself solved compared to P. And so it's sort of like, it leads to an ordering of the minus momenta here, so that I have P1 minus much greater than K1 minus much greater than Q2 minus, and I have a decreasing direction of minus momentum this way. If I work out the kinematics correctly, then I should have an increasing amount of plus momentum that goes the other way, such that basically every gluon is at mid rapidity compared to its parents on either side. Sort of the idea is that I get a boost invariant distribution anywhere, anytime that I'm here, anytime that I'm very far away from the endpoint of my sources that are moving at the speed of light and generating these. So the logarithmic evolution comes from saying, what if I have high energy scattering at one energy S, let's say a small value of S, so to speak, where this is my amount of rapidity to radiate gluons here. As I increase S, now my plus going particle moves a little bit further in the plus direction, minus going particle moves a little further in the minus going direction, and now I have a little bit extra phase space. And so as long as I have this guy is radiated in the new slice, and all of these are radiated at something much softer, then I don't know, they're all ordered with respect. So what I'm trying to say, as long as I satisfy this ordering condition of the momenta, then I guarantee that every time I have another alpha S, I'm going to generate another log of S over X. So it's not guaranteed, but there is a sector of phase space, that strongly ordered sector of phase space that continues to generate that ordering condition so that you have the large phase space at every step. Does that help?
Yes, thank you.
Okay, great. Okay, so the picture that starts to emerge with high energy scattering from this discussion is that you have highly boosted kinematics, where I might have a ultra-relativistic particle moving with large momentum P1 minus. It might radiate a gluon, and then I have an interaction vertex that happens at very short distances. So I mean, over very short time scales. So for instance, we drew a diagram that looked like this one. And if I think about the space-time structure of this diagram A, my particle moving with large P minus can have radiated this gluon anywhere in the infinite past. I'm really integrating over the time of emission of that gluon anywhere from T minus infinity up to T equals 0, right when it hits with this gluonic interaction in the time. So that is, in a very literal sense, a time-ordered wave function you can quantify. The other thing is that we saw that the kinematics of this gluon were practically instantaneous. So this one we saw Q plus and Q minus were basically 0. So that this is like an instantaneous shock wave almost interaction. Shock wave is maybe a little bit of a strong term for a single puny gluon, but we're going to buff it up in a minute here. Both the Q plus and the Q minus were 0. So this is a gluon which is neither propagating, so to speak, in the plus direction nor in the minus direction. It's sort of a local instantaneous interaction. This gives us this picture of what's happening in the scattering as like a time-ordered interpretation, where I have dynamics that happen from T equals minus infinity to T equals 0. At T equals 0, a scattering occurs. And then after t equals 0 out to t equals infinity, I may have other final state emission. So for instance, this diagram B, where I have the scattering here, say at time 0, and then I have a whole infinite amount of time after the fact in which to radiate that extra gluon. So the first thing that comes to mind is the kinematics. That this process at very high energies is naturally time ordered, but it's not time ordered in the sense of clock time, it's time ordered in the sense of light front. So high energy scattering is naturally time ordered, quote unquote time, along the light front. And this is maybe a different way of reinterpreting the 5 diagrams that we just calculated. So we said for the NLO quark production, I have this process, this initial state process, I would represent as the wave function for my incoming quark to split into a quark plus a gluon, long in the distant past, anywhere from -infinity to 0. And then later on, it just so happens that this quark is the lucky fellow who gets hit by a gluon from the target. I also have diagram B. Diagram B was the final state emission diagram. So this one would look like scattering at t equals 0, and then the final state wave function for the radiation of that. There's one other possibility for radiation off of the projectile. If I think of this time-ordered picture, I can radiate in the early time, and then the gluon could be the lucky fellow who scatters. That diagram is this one. But this is just another way of drawing the diagram where it's that 3 gluon vertex in the center there. So the process lends itself naturally to a time-ordered interpretation. This is just another way of interpreting the same diagrams that we calculated before. If I work in a symmetric gauge like Feynman gauge, then I have both radiation off of projectile and target, and then it's kind of messy because I have to deal with both plus directions and minus directions, which are both large at the same time. But it's much more helpful if I pick an asymmetric gauge. So if I pick, say, a minus equals 0 gauge, I think in this notation, then I forbid radiation from the target, and then these 3 diagrams are the only 3 diagrams. So this sort of lends itself to a picture where high energy scattering looks like semi-infinite wave functions. Wave functions that describe whatever my initial state is that splits into something. I have scattering operators which show up in the form of T-channel gluon exchange. The essential building block was that elastic quark-quark scattering process that we calculated. And then in my final state, I may have wave functions conjugated, so to speak, that describe, I don't know, fusion into a J psi from a virtual photon in diffractive scattering at ES. So this is sort of the natural language that falls out of both primarily of the kinematics of high energy scattering. The second thing that lends itself very nicely to this wave function scattering operator, wave function perspective, is that haunting notion that there could be a very large density of gluon. So at this level, we've done single gluon scattering. And if I was working in ordinary perturbation theory, then that's all I would worry about. I would say, oh, I have 1 gluon scattering is all I need, because double gluon scattering, that would be higher order in perturbation theory. So if this is order alpha s, then this would be order alpha s squared. And if I have 3 of them, then it's even more simple. So I don't need to worry in my standard perturbation theory, my vacuum perturbation theory. I don't have to worry about all of these higher order corrections unless I'm really going for extreme precision. But that changes if there's the possibility that I have high occupation number of these gluons. Every time I bring in another gluon here, I pay a price. Maybe let me write it this way instead of doing alpha S. Let me say I have A here, A mu here, and I have a vertex here that brings in a coupling G. So this insertion is order G times A. Normally A is an order 1 quantity, so this is determined by G, which is a small number. 2 of these insertions would be order B squared, A squared, 3 of them would be order G cubed, A cubed. And if we have G much less than 1, A is of order 1, then this means that this diagram outweighs this diagram outweighs that diagram. But the threat or the promise of the high gluon densities is that we can reorder this perturbation series. If A is not order 1, if A is large, if A is order 1 over G, then G times A is not small. G times A can be order 1. And in that case, 1 gluon exchange or 2 gluon exchange or n gluon exchange is all equally probable. Because I have such high gluon density, such availability of gluons to encounter, it offsets the low probability of interacting with any one of them. So this is sort of the framework that we'll use now to construct and try to understand the evolution equations that govern gluon saturation. We can write down cross sections in terms of a scattering operator at some initial energy. And then we can calculate a gluon radiative correction to it. And then we get an expression in terms of a new scattering. So that's the basis for the recursion relation that will encode these large logarithms and that we want to solve. So I had wanted to go through a nice derivation of the Wilson line itself, but I don't think I have all of my notes together to be able to do it. The punchline is that the Wilson line that describes that propagation, the resummed propagation. The Wilson line is a path-ordered exponential that integrates the vector potential A mu. So you integrate it, if I'm going, let's say, in the light cone plus direction, then I integrate dx plus A minus A TA, where A minus is evaluated as A minus A at the point x plus, 0 minus, and x perp, whatever x perp your Wilson line is fixed. So, okay, maybe let me unpack this a little bit. Another thing that's very nice about high energy kinematics, another thing that makes this time ordered picture so appealing, is that because the interaction is so length contracted. Let me take a point of view where I put the relativistic effects in the target so that this is now length contracted. It's contracted essentially to a delta function, something that is instantaneous at time equals 0. Sorry, I lost my train of thought for a second there. The target is contracted to a delta function. Transverse coordinate space. So the point is that the interaction essentially takes 0 time. So even though I'm scattering in the medium, I'm transferring some transverse momentum from projectile to target. That momentum exchange happens effectively instantaneously. So it's like an impulse where my particle comes in with some, let's say, transverse position to begin with. It suddenly acquires some momentum and it goes out with a new momentum Q perfect it didn't have before. But since this didn't take any time, the particle doesn't have time to drift its transverse position. So it picks up that extra transverse momentum, but its actual transverse position, x perp, is exactly the same coming in and going. So it's especially advantageous to formulate this as wave functions and scattering operators in position space, because those transverse positions are fixed throughout the scattering process as a consequence of its instantaneous kinematics, the fact that it takes 0. It's quite non-trivial to see how the Wilson line works out for something like the Eichenal quark. We calculated what happens if I had a quark scattering at high energies. We basically saw that at this vertex, we get a large, I think in this direction, we had a large P minus. So we ended up with a P minus and then the A plus component of the field. The A plus component of the field was computed from the quark down here in the top. So we computed this and we found that this was unsuppressed at high energies. Why is it still unsuppressed if I add more? If I add another scattering, then I'm going to have another factor of P minus A plus, but I'm also going to have a propagator in between. Essentially what happens is you do a Fourier transform of this expression as a function of the distance. Let's say if this is at position 0 and this is at position x plus, then I do a Fourier transform over that distance, which is conjugate to the minus momentum. Let's say if this is momentum L, then it's the minus momentum going through that line. The punchline is that you do the Fourier transform and you pick up the pole that puts the intermediate state on shell. So then this reduces down to the same U bar A slash U, U bar A slash U that we had before in the single port level. And after you pick up the pole, there's a residue. The residue is 1 over 2 P minus. So essentially what happens is from the vertex, you get a factor of P minus A plus. From the residue, or from the time separation, essentially, you get 1 over P2 minus, 2 P minus. So all of the kinematic factors cancel between numerator and denominator, between the propagator and the extra vertex insertion. So even though every time I do this, I pick up another factor of P minus A plus, I immediately kill the P minus down here. And so I end up just with a series of position ordered insertions of the A plus field. I can only, by the way, collect this pole if the positions of these two vertices are ordered in the correct way. So this comes, for instance, with a conditional step function that I only get this pole if x plus came after 0 plus in this equation. So these are the ingredients that essentially go into building up the Wilson line. I believe Thomas already derived this for you, at least in the scalar context, but this is to show that it still continues to work essentially the same way in a spare. Okay, so one other interesting comment to make perhaps about this time-ordered picture is that it even works as a way of implementing the virtual correction. We've talked about the leading order elastic scattering cross-section, QQ to QQ. When we talked about MLO, we only talked about the real corrections. Quark goes to quark glue. But in principle at MLO, there's also the one loop correction to quark goes to quark. At one loop. These corrections include things like loop corrections on the external legs that change the normalization of the states. They also include vertex type corrections. Things that go around the vertex like this, and then things that in QCD participate in the vertex like this. These are things that can still, again, be interpreted in terms of the light front wave functions. It may not be obvious how that works. I'll come back to this one in a second. These guys, it's interesting to note, are described in terms of the same light front wave functions, that same splitting amplitude for the quark to split into a quark and a gluon, just at the amplitude level, before and after. So this one looks like incoming quark, and then you radiate a gluon. This first diagram is the one where then it's this particular quark that does the scattering. So this looks like wave function conjugate. And then I have the scattering that takes place on the quark in this case. This one is the one where the scattering takes place on the gluon. So the virtual corrections also sort of fit within this time ordered point of view. Another useful connection is that you can get the magnitude of this virtual correction, the correction to the normalization of the state, by enforcing unitarity from the real corrections. Right, so I think I can get this right. So if I use this light front wave function description to write down my quark state, including that virtual correction. So let's say I have a quark state with momentum p. The dressed quark state, after including all of the self-interactions in perturbation theory, consists of a bare quark state with momentum p. So that's what I have at 0th order in the coupling. At first order in the coupling, order G, I can have production of a gluon in the final state. So then I'll have a quark with momentum P minus K and a gluon with momentum K. And then this comes along with a wave function for that real emission that describes the kinematics in terms of P and K. And then I have to sum and integrate that wave function over all of its quantum numbers and all of its fixed. So this is order G to the 0. This is order G to the 1. At order G squared, I have double real emission. But that's, if I square it, that's beyond the accuracy that I need. The term that I need to keep is the virtual correction to the single quark. So now there is a virtual correction which includes these kind of self-interactions at order G. And then everything else is higher order in perturbation up to order G. So the relation between the real and the virtual parts comes from enforcing the normalization of the states. I need the dressed states to be normalized to a delta function. So that if I have a quark with momentum P prime and a quark with momentum P, these things should be normalized to 2 pi cubed 2 EP delta 3 of P minus P prime, as well as Kronecker deltas for the other quantum. The spins. The dressed states satisfy this. But the bare states also already satisfy that at 0th order in perturbation. So essentially that means if I take this expression and I square it, the trivial term already accounts for all of the normalization. And all of the other terms that I add in have to give me 0. So in order to ensure that that both of these conditions are satisfied, that the exact normalization is true, and that the normalization at each order in perturbation theory is satisfied. Then it means that all of the NLO corrections to that norm must be 0. So the sum of the real and the virtual corrections that comes in must be 0. When I add these pieces and I square it up to order G squared, then what I find is that the sum of the virtual correction plus its complex conjugate plus the sum and the integral over all of the real wave function emissions squared is to give me 0. So there is a unitarity constraint that says essentially any probability that I add into the 2-particle sector of the Fock space, I must subtract from the single particle part of the Fock space in order to conserve probability. So if I put 10% weight in the quark blue sector, I have to add this piece whose job is to subtract off the matching 10% probability from the one blue sector. So, sorry, the single particle sector. So the point is that these light front wave functions are the universal building blocks of all of this high energy scattering. You can use them for the real corrections. Through these unitarity relations, you can also use them for the virtual corrections. All you need now is to staple them together with the high energy scattering operators, which in general are the Wilson. Those are the most general types of interactions that a particle can have at infinitely high energy for arbitrary number of scatterings and everything else. So that really sets the stage for how to do the calculation of scattering at high energy and how to calculate the evolution. So I have mentioned how important these light front wave functions are. I should probably show you one. So the one which is the universal building block for our small x evolution is the one that describes a particle with momentum, let's say P plus and transverse momentum P perp, that then radiates a gluon whose momentum is x P plus in the longitudinal direction, and it has some transverse momentum K perp. And then it produces a scattered quark whose momentum is 1 minus x P plus P perp minus K perp, with minus components set by the on-shell condition. I guess if I assign quantum numbers to this, my initial spin is sigma, my initial color is I, final spin is sigma prime, final color is I prime. The polarization of the gluon is lambda, and the color of the gluon is A. The definition of this light front wave function, which is in general a function of the momenta P and K, it's defined as GTA U bar of particle P minus K, epsilon slash lambda star U of particle P over 2P plus P minus minus K minus minus P minus K minus, where these are the on-shell values. For instance, P minus K minus means P minus K perp squared plus M squared over 2 1 minus X plus, for instance. So this wave function may not be obvious, but this is actually a very familiar thing. My PhD grandfather, my PhD advisor's PhD advisor, Al Mueller, calls it old-fashioned perturbation theory, because that's what it is. This is just ordinary time-ordered perturbation theory in quantum mechanics. So you can really think of it as the amplitude to go from something in the past to a different state in the future. The time-ordered perturbation theory includes an energy denominator. If you were doing time-ordered perturbation theory in ordinary quantum mechanics, you would have 1 over delta E, meaning 1 over the initial energy that you start off with in the state you are asking about, and then if it fluctuates to another state, you subtract the energy in the final state. You're allowed to violate energy conservation due to quantum fluctuations for a short period of time. And the amount of energy violated due to that quantum fluctuation is what sets the lifetime fluctuation. This is exactly what's happening here in the light front, except that the energy is, the role of the energy is being played by the minus. So this is appropriate for a particle moving with a large P plus momentum, and then the P minus plays the role of the energy. So 1 over this difference is the typical lifetime in light front. So delta X plus would be 1 over this delta P minus, the violation of minus 1. So when you write this thing down, you can evaluate the whole expression in light cone gauge. It has a particularly simple. So if I evaluate that light front wave function, I get 2GTA I prime I, atomic or delta sigma sigma prime. I get square root 1 minus X times the quantity 1 minus X delta lambda negative sigma times epsilon lambda star perf dot K minus X P perf over K minus XP perf squared. So this is for arbitrary kinematics. I haven't yet made the assumption that this gluon is a soft, that X is much less than 1. You can see sort of the general structure of the wave function. One thing that you notice immediately is there's a Kronecker delta of the spins. That's because I'm working in the massless limit. And in the massless limit, helicity is a conserved quantum number because it's identical to chirality. So the sheer fact that it's massless guarantees that I'm going to have delta sigma sigma prime. I have some prefactors that depend on x. This prefactor depends on x. The factor in brackets here is kind of interesting. This is the one that tells me how the amplitude depends on the spin of the gluon. There is a Kronecker delta here that prefers to have the gluon in a particular orientation. The spin configurations of this process are interesting. Whatever spin the initial quark has is the same the final quark has, so angular momentum is already conserved by that. And basically what this expression does is it gives you either +1 unit of orbital angular momentum and -1 unit of gluon polarization, or the other way around. There's a bias for one of those polarization preferences, but that bias goes away at small x. So the full wave function has interesting spin structure, but if I take x goes to 0, the small x limit, all that goes away. That prefactor goes away, and even my momentum dependence simplifies. There's so much more to say about like front wave functions. So for our purposes, the most useful thing is the small x limit of that wave function. So for x much less than 1, my wave function only depends on k perp and x, and I get 2g ta I prime I delta sigma sigma prime epsilon lambda star perp dot k perp over k perp squared. And as I said before, it's super useful to go directly to coordinate space rather than momentum space for the purposes of combining together wave functions and scattering operators. So if I perform the Fourier transform of this operator to position space, then psi as a function of, let me call it r perp, and the momentum fraction x is igta I prime I over pi delta sigma sigma prime epsilon lambda star dot r perp over r perp squared. So in particular, the transverse position wave function is the fundamental building block that we'll need to assemble BFK. Okay, how am I doing on this? Okay, I am noting the time. We've got about an hour left. I think at this point, I'm going to switch to showing some of the material that was on the slides that I sent. There may be times that I'll pause and go back to the Blackboard to explain something in greater detail, but I think right now it'll be very valuable to have all of the images on the slides. So let me go to that. So before constructing and solving BK, I wanted to make a point about how to relate the cross sections that we're talking about for high energy scattering to the parton distribution functions, which is how people normally discuss gluon saturation. That requires at least a few minutes discussion of deep inelastic scattering and how it works. Deep inelastic scattering is, in a very literal sense, using a collider scale electron microscope. And I mean that in a literal sense because an electron microscope is just using the wavelength of an electron to perform imaging on a target sample. That's exactly what a scanning electron microscope does. The only difference is that a scanning electron microscope uses electrons with thermal energies. Whereas if you untether it from the laboratory, then you can use the full collider energies, bring those to bear. So that is deep inelastic scattering as performed, for example, in Hera. You're looking at inclusive electron-proton scattering. Quick history, the first DIS experiments were done at SLAC. These were the experiments that essentially discovered QCD in 1968 or so. The highest energy electron-proton collider ever built was the Hera accelerator. That reached center of mass energies of more than 300 GeV. And we are eagerly awaiting the construction and activation of the electron-ion collider, which, even though not quite as high in energy as the Hera collider, will have tremendous other abilities in terms of polarization and flexible ion species to allow us to look at high densities with high precision.
Sorry, I have a question.
Yes, please.
What's the difference between beam energy and center of mass energy?
The center of mass energy is much lower than the beam energy. Loosely speaking, your center of mass energy is like a square root of the beam energy times the mass. Between a fixed target experiment and a collider experiment, you pay a big hit in the center of mass energy by having one of the particles at rest. So I don't know off the top of my head what that is in terms of square root of S. I have to do the conversion. Square root of 20, I guess. Does that answer the question? No.
Water come from both ends, right? You are in the center of mass system with your detector if you have like particles. And fixed target, well, sits here.
Yeah.
One of them doesn't contribute, right?
So when you boost from the fixed target to a center of mass frame, you're boosting to a frame where the beam energy has much lower. Beam particle has much lower energy because you need to boost the fixed target to have a opposite.
Yeah, exactly.
So you're going to
The center of mass system in a fixed target experiment has the detector flying towards you, right? Okay. I think we're good. Matt?
I think the demonstration is the definition of center of mass energy S, or Mandel-Stem S, is P1 plus P2 quantity squared. So in the center of mass frame, if I have two particles coming at each other with energy E, then the sum of these two things is 2E.
Oh.
I'm sorry?
Matt, would you share the other?
Oh, I'm sorry, I'm still showing the slides.
You're still showing the slides, yes.
Yes, okay, sorry. Right. So S is P1 plus P2 quantity squared. If I have a collision process that's taking place in the center of mass, then I have two particles coming straight at each other with energy roughly E. One of them is E0 positive E along the z-axis. The other one is E0 negative E along the z-axis. If I add P1 plus P2 together, the energy terms combine. Everything else gives me 0. And then when I square it, I get 4 E squared. So this is my energy in the center of mass. And energy in the center of mass frame is just square root S over root, so root S over. That's if I'm in the center of mass frame, where sort of all of the energy which is in both particles is going to dump directly into S. But you pay a huge hit if one of the particles is at rest. So now if I have rest frame, if I have P1 mu is E0 per E, but P2 is at rest, that's M and then nothing. Then when I add them together, I get E plus M 0 per E squared. So then I square it, I get E plus M quantity squared minus E squared. I cancel my biggest term, the E squared piece, and I get 2ME plus M squared for S. So this is my E beam. So there's a huge difference between E beam equals 20 and root S equals 20. If E beam equals 20, maybe let me throw away the mass squared for simplicity. Yeah, so my root S in this case would be root 2ME beam. Whereas here my root S is, let's let it again. Root S is 2 times E center of mass. So if you have a collider experiment, all of the energy in your beam is directly proportional to root S. If you have a fixed target experiment, then you have a square root relationship between the beam energy that you're providing and the actual center of mass root S you get out. Because basically you're taking a geometric average of something with energy E and something with energy M. So you highly dilute your energy in a fixed target setting. Does that help?
Yeah, definitely.
Okay, great. Okay, so back to DIS. So this is sort of the evolution of DIS from its first days where we discovered QCD to the near-term future in the EIC. We've talked extensively about gauge theories and how gauge theories communicate. So in terms of using DIS to discover QCD, if you didn't know what was inside the proton, you would still know that my electron is going to interact with it by a vertex of the form J mu A mu. I know that just because the photon is a gauge particle. So the measurement of deep inelastic scattering tells me something about matrix elements of the electromagnetic current inside the proton. The amplitude has one electromagnetic current, so the cross section, the amplitude squared, has two. There are sort of two parts to the overall cross section. One part is the QED part, the part associated with your electron emitting the photon. That is simple and straightforward. You can calculate it in QED and remove it. The interesting part that we really care about is that hadronic matrix element of the electromagnetic currents. If you don't know anything about what QCD really does, this is about as far as you can go, and you have to measure that correlator experimentally. What are you allowed to see when you measure that correlator experimentally? DIS depends on two kinematic variables, just like we were talking here in terms of Mandelstam S and T. There are analogous variables for DIS. The transverse variable analogous to Mandelstam T is Q squared. That's that momentum transfer associated with the photon. The Q squared is Fourier conjugate to the transverse distance. So Q is really like a resolution scale. Tells you the amount of transverse resolution you can see inside the proton. If your Q squared is much bigger than the mass of the proton, 1 GeV, then you're really resolving quarks and gluons inside the proton. X is a longitudinal variable. This is related to Mandelstam S. And we said that this is, it's a measure of the boost. So one way of expressing the time scales or the resolution scales for X is in terms of a Yoffie time. The amount of time that you resolve the interactions of the proton. So in terms of a metaphor to a camera or a microscope, there's two scales. There's the pixel size or the resolution, and then there's the shutter speed or the exposure time. The time is different than the resolution, but the time matters. That determines whether you are able to resolve short-lived quantum fluctuations if you boost them enough or not. And so that's a knob that you can dial between looking at the long permanent properties of the proton versus looking at the temporary quantum fluctuations instead. Okay, question?
Right. So this sort of analogy that you've made with a shutter speed. So the small
Yes.
x kind of corresponds to long timescales. Is that?
Yes. So the smaller x you go to, so this time scale, think of it like the boosted interaction time. So if something would have happened on a particular length scale, a particular time scale in the rest frame, you've boosted it by a huge gamma factor. So now you have the ability to see. The metaphor in terms of the shutter speed kind of goes the other way. It's the higher the energy, the bigger the boost factor. And so then you take what used to be a short-lived quantum fluctuation and make it much longer-lived because you enhance its lifetime. You can view the process also differently in different frames. You can either talk about it as Lorentz contraction or time dilation, that they're equivalent. Does that help? We're talking in circles.
Right. It's just when we spoke about interactions, you stress that these interactions are mainly instantaneous. So
More and more stuff looks instantaneous as you go to smaller and smaller.
Yes, so that's a good point. Precisely what I'm talking about here, like this time scale is a time scale at the level of the amplitude squared. I'm not sure how to say it in a simple physical way, but what let me go back to the board again. So the precise technical statement here is that the separation between those currents, we had J mu of X and J nu of 0. The separation from these things is Fourier conjugate to the momentum of the photon. So you've got d4x e to the minus I q dot x, where q is the photon momentum. Q mu has a component which is negative Bjorken x e plus, a large q minus, and 0 perp in bright. So where does it come in? It comes in through this Fourier transform. Really what I mean is I'm talking about the separation of these two operators at the level of this forward matrix. So I don't know if that helps understanding, but maybe this equation is the one to point to for W mu nu here, that Bjorken x is in one of the components of Q mu. So if Bjorken x is getting small, that means I'm looking at the behavior of this current correlation function when the two currents are separated by a very long distance in a light direction. But it's kind of a weird thing. You're right to point it out about the time scales, because this is a scale of the amplitude squared. There's also a difference in the scales in x plus and x minus. Maybe that's the better answer to your question. For the scattering that's happening primarily at large P plus, then that large P plus is Fourier conjugate to the separation R minus. So I would say there's a large separation in R minus, but the thing is local in X plus, delta of R. So we had, let's see if I can get this right. So if I have a particle moving with a large, I'm sorry.
We still see the slide.
Damn it, I did it again, I'm sorry. Okay.
This is hard to keep straight.
Yes. Right. So I'm trying to say, if the particle has a large P plus, then the wavelength that I'm talking about here is R minus. Okay, that's probably the way to say it. The P plus is large, so this thing is localized in R minus. I'm talking go along like plus direction, it should be time, yes, integral dx plus a minus of x plus 0 minus x, right? It's all there in the Wilson. So I have something which is half ordered over some separation in x plus, but it's highly localized in x minus. So I think part of it is that I'm talking about two different time scales here. One of them is a plus time scale, where I have potentially a large separation of these currents along one of these directions, but it's sort of narrow in the other. I'm sorry, this is not a satisfactory explanation. I'm sort of chasing my tail trying to pin it down for you. Maybe I'll move on and then we can come back to it if there's still some confusion.
Sure, thank you.
Sorry. So I was, with the point about this time scale, I'm trying to motivate what changes as you change X. I want to give you some intuition for what X means. And the idea is that as you go to smaller and smaller X, you will see more and more of the quantum fluctuations, because smaller X means higher energy, higher Mandelstam S, and therefore higher boost factor. Okay, so this is related to how QCD was discovered. I won't belabor that. The important point that comes out of it is the picture of the proton we see. When you do deep inelastic scattering many times, you can reconstruct the distribution of what you hit. And every deep inelastic scattering event gives you sort of one data point on the X value that you saw inside the proton. The proton at large X looks more or less like you expect it to. It is made up of mostly up quarks and down quarks, about twice as many up as down. The typical X value of the valence quarks is sitting around X of 1/3, which is exactly what you would expect if the proton was just 3 quarks sitting at rest, all sharing an equal momentum fraction. But that's not all that's going on. They don't have exactly 1/3 of the momentum. They bleed off some of their energy into radiation because QCD is a dynamic theory. And we see that as a function of x, as expected, the gluon density rises very sharply. Note that this is a logarithmic scale. That's the only way to fit the valence distributions and the C and glue distributions on the same plot without cheating. So the point of this is that there are two very different regimes of proton structure. The large X regime is the dilute regime when you have few body physics. But the small X regime that we've been discussing here is completely different. It's dominated by that gluon radiation. And that actually shows up in the structure of the proton itself. So it's a little bit more subtle than this. You can't just look at the gluons exploding and say, aha, that is small x gluon explosion as predicted by the theory of small x. The theory without the small x limit, without these logs of 1 over x, already includes some of that behavior. But it's interesting to note that if you try to fit this data without logs of 1 over x, without small x effects, you see a systematic breakdown in the fits. So that's what this rightmost plot is. I like this one very much from the Hera PDF folks. This is the quality of their fit to the data, assuming in green, not small x physics, assuming only standard large Q squared D-lab physics. And you see that it works, but that as you go to smaller and smaller x, you include more and more low x data, the quality of the fit breaks down. There's something systematic happening at small x here. And what they show is that if you include the logs of 1 over x that we will construct in a moment, that cures this problem. So it does seem like just at the level of the PDFs, if you take sort of a strict interpretation, you cannot get away pretending there is nothing at small x. You need some amount of small x resummation already to describe the Hera data. And that's perhaps a hint of things to come at higher gluon densities. Okay, so this is about where I stopped on the blackboard. We talked about Wilson lines as the scattering operators. The Wilson lines show up in a very literal way for deep inelastic scattering. For deep inelastic scattering at large x, what happens is that your virtual photon comes in and it knocks out a quark that has x p plus worth of proton momentum. And we said that the valence quarks have x sitting close to 1/3. So if my photon comes in that happens to have x close to 1/3, then it can knock out a valence quark. And that's sort of the typical picture of deep inelastic scattering at, let's say, Jefferson lab energies. But if you go to much, much higher energies and much, much lower x, you run out of valence quarks. If I have a photon that comes in with x of 10 to the minus 3, there aren't really any valence quarks with x of 10 to the minus 3. And so in that case, instead of this knockout process, you become dominated by the next to leading order process. So basically what I'm saying, let me see if I can sketch on my screen here. What I'm saying is that this process on the left is leading order in the alpha S power counting. But the problem is that this thing is proportional to x as x goes to 0. And that's more or less just because the valence quark is proportional to x as x goes to 0. So this leading order process, it's leading order in alpha S, but it doesn't help you at all when x goes to 0. When x goes to 0, you're taken over by a dipole channel, which is higher order in alpha S. It's got an extra alpha S in it compared to the leading order process. But it is independent of x because it's mediated by gluon exchange. And as we showed, the gluon exchange is unsuppressed no matter how many of them you have. So something qualitatively different does happen to DIS at small x. You switch from a knockout process to a dipole scattering process, where really your PDFs, like the DIS cross-section and therefore the PDFs you get from them, are literally derived from the physical scattering of a quark anti-quark dipole coming from the DIS virtual photon that then interacts with the proton according to this Wilson. So when we talk about dipole evolution, you can think of it in a very literal sense for deep inelastic scattering, that you're starting off with a single QQ bar dipole from the DIS virtual photon. And now we can dress it up with all of those extra wave function corrections that can happen. Right, so this was the connection that we just made. The scattering part that is the building block for the Wilson line comes from that iconal elastic scattering that we calculated. And then the higher order radiative corrections come in with the large logs with the same origin that we saw from the inelastic port. Okay, this is just the point that in solving for the energy dependence of the cross sections, you're also explicitly getting the X dependence of the PDFs. The behavior of one gives you the behavior of the other. Okay, so if I take deep inelastic scattering and I think about it in terms of this small x time-ordered picture, my virtual photon comes in and it has a long lifetime, and the interaction with the target happens highly localized in X plus. So my virtual photon can fluctuate before or after. Maybe let me go to the board for this. The image on the slides there is more in terms of an operator notation. Let me go to the actual scattering. So if my wave function picture is virtual photon gamma star comes in and it fluctuates into a quark anti-quark pair, and then somewhere after that I have a Wilson line that describes the scattering of a quark at some transverse position x, scattering of an anti-quark at transverse position y. 1 over NC, trace of the x vy there. If it's the QQ bar dipole that passes through the shell. So this is the case if I have initial state splitting and then a final state interaction. So here I would get wave function times trace the x vy dagger for my scattering. The other possibility is that I could have the virtual photon is what passes through at time equals 0, and then the splitting happens after that. Here the scattering operator is trivial, it's 1, so nothing really happens. And I have the wave function in the final state that comes with a minus. So here I get minus the wave function and the identity. So I have these two choices for the wave function in the amplitude, and then I have the same set of choices for the wave function in the complex conjugate amplitude. So that's how I get 4 possible terms. Yep. So the one where both splittings happen after the shock wave, which is this blue line here, that has nothing for the interaction. I also have something where both splittings happen before. Here I have interesting Wilson lines, but they cancel. I have Wilson line Vx, Wilson line Vy dagger, and then I have Wilson line Vy, Wilson line Vx dagger. So again, let me go back to the board of this. So I think it's straightforward to see that for the time ordering where the shock wave is here, final state cut, shock wave is here, I get identity operator, and then my wave function. What's maybe less obvious is that if I have this time ordering where my Wilson line shock waves happen after in both cases. Here the interaction comes as a trace. So let's say if this is position X perp and this is position Y perp, this is the quark line, this is the anti-quark line, and then when I complex conjugate these things, I get the opposite Wilson line in the conjugate. So this object has trace of Wilson line Vx for a quark at position X perp. Then I have Wilson line for the anti-quark Vy perp dagger. And then in the complex conjugate amplitude, I have the opposite of this. I have the opposite scattering at the same transverse position Y. And then I have the conjugate Vx per dagger. And so these guys just cancel each other. So the sort of the squared cases, the diagonal cases, give a trivial scattering. So I get 1 from the first diagram up here. Let me sketch again. So this expression contributes a 1. This expression contributes the other 1. These two expressions here, these two time orderings have a scattering amplitude in them. So this has a dipole with here, quark is at position x0, the anti-quark is at position x1. And then this one is the complex conjugate of that. So the overall scattering operator, when I add up all four diagrams, is two different combinations of dipoles. And then everybody has the same wave functions, the same light front wave functions to split that virtual photon into a quark anti-quark pair. So that's sort of the starting point, is that you can get PDFs and you can get cross sections in terms of those Wilson line scattering operators. Okay, you can choose initial conditions for the scattering operator. The really interesting thing, though, is now when I ask for quantum corrections to the scattering operator. So now let me go back to the board again. So really, regardless of what context you're talking about, the scattering operator that is the basis for high energy scattering in QCD is this type. It shows up in DIS, it shows up in proton-proton collisions, it shows up everywhere. So to formulate how the quantum evolution works, you really want to ask, if I start off with something that is a dipole operator at position X perp, antiparticle at position Y perp, and it passes through the shock wave. This means I'm looking at the trace of Wilson lines Vx, Vy dagger at a particular scale. So if I calculate high energy scattering at some energy S, which is what defines the strength of that Wilson line. Now if I add S plus a little bit, then I should see one logarithmic step of evolution. So if I add just enough extra center of mass energy S to get one extra logarithm, then that's enough to offset 1 power of alpha S. So I can look for corrections to this process coming from a gluon emission in all possible ways that connects this type. So I can have things like a gluon that is radiated from the quark line, passes through the shock wave and interacts, and then gets reabsorbed. And I would describe this process as the wave function for the quark to emit the gluon. And then I would have a scattering operator that contains not only the quark Vx and the anti-quark Vy dagger, but I would also have a new Wilson line for the gluon. This would be an adjoint Wilson line. It's the same path order exponential as the quark Wilson line, but using the the adjoint color representation instead of the fundamental. So the strategy is start with a single QQ bar dipole and consider gluon loops in all possible ways, the addition of these soft gluons. I'm only going to look in the corner of phase space that actually generates alpha S log 1 over X, or equivalently alpha S log center of mass energy over M squared. It's all going to be built out of wave functions. The wave function to emit either from the quark at X or the anti-quark at Y. I'm going to have complex conjugate wave functions for how they can be reabsorbed in all possible ways. And then I'll have my scattering operator, which will depend on, does that extra gluon go across the shock wave like this, or does it get reabsorbed before? If it crosses the shock wave, I have a new Wilson line, a different, more complicated scattering operator than the dipole I started off with. If it gets reabsorbed as a virtual correction, then I have the same dipole operator as before, just at a different scale. So that's the strategy. We want to enumerate all possible diagrams. We have the ingredients of the wave function so that we know the form of the integrals. The trick now is to assemble the overall kernel and understand its structure. So let me go back to my slides. Okay, so let's build all of the ingredients. The diagrams come in several different classes. I said some of the diagrams have the gluon which crosses the shock wave. So these are the diagrams where the emission point was before and the absorption point is after. Here, these come in with a new, more complicated scattering operator. So as I said, now instead of just the trace V dagger, now there's the color matrix that emits the gluon, the adjoint propagation of the gluon through the background field, and then the color matrix that absorbs it. So I've got a TA and a TB for the absorption and the emission, and the U is the gluon-Wilson line with final state color B and initial state color A. So this would be A, B, and then this is U, B, A, where there's a new transverse position describing the location of that gluon, and that has to get integrated over in the current. So some of the diagrams are real diagrams where I have a more complicated scattering operator. The virtual ones are just proportional to the dipole amplitude, and then I get a color factor from the gluon loop. So those are sort of the type of scattering operators that will enter my equation. Not my equation, I didn't invent it. In terms of the wave functions, there are two non-trivial ways that I can combine the wave functions. Maybe three, depending on how you count them. One way is that I can emit and absorb from the same line. That's a wave function squared term. Recall that we wrote the wave function in position space. Psi was proportional to epsilon dot x perp over x perp squared. So that then when you square this thing and sum over all of the polarizations, you get something that goes like 1 over x perp squared, where that x perp is the size, the distance of that fluctuation. So it's easy to see where a structure like this comes from. This is a structure that's a wave function squared emitting a gluon from particle number 1. And then I have something similar for the emission around particle number 2. So I get those sort of perfect square terms in the wave function. I also get cross terms. The cross terms do not look like 1 over distance squared. They look like a dot product. And that's because it involves the distance x2 minus x1 on one side, x2 minus x0 on the other side. There are 2 of them because I can have the gluon go one way or the other way. And notice that it also differs by a minus sign. You can understand that minus sign is because the charge of the quark is plus G, the charge of the anti-quark is minus G. So whereas the charge of the quark or the anti-quark gets squared in the perfect square, and it doesn't matter, in the cross term it does, such that it comes in with a minus sign. So these are the ingredients, oh, wrong button, sorry. These are the ingredients to build the evolution equations. Let me maybe point to the final form of the evolution equation, and then I'll take a step back and show you where the pieces came from. So this is one way of expressing the evolution equation. This is the integral form. What's being written is, so on the left, this is the evaluation of the dipole operator at a particular scale CS. This term is the initial condition. And then this integral term is the one that generates the large logarithm. The large logarithm here contains the alpha S in front, and the log is here explicitly in this dz over z integral that comes out of the wave functions and the 2-particle wave space. The scattering operators here have been simplified a little bit. If I go back here. So there's a nice trick that you can use to simplify the color algebra of this gluon-Wilson line. The gluon-Wilson line can be written as a trace involving the fundamental Wilson lines. It's just a color representation statement. So this U2BA is the same thing as 2 times the trace sorry, 2 times the trace of the Wilson line V2 TB, V2 dagger TA. So you can relate the color indices here to insertions of the fundamental matrices TA and TB, and then the gluon shows up as a V times a V dagger. That's the substitution that's been made for these real corrections. And then the repeated A's and B's can get simplified by using the Sievert identity. I showed that before. So that's how the scattering operators get simplified down completely in terms of dipoles. Everything becomes either a single dipole. This one on the right is essentially the virtual terms. And then the term involving the gluon gets converted into a double dipole operator. So you see this one involves actual scattering at position number 2. That's the scattering of the gluon after the color algebra has been massaged. So this characteristic form of the BFKL kernel is actually the summation of these two effects together. So if I have my scattering operators and I have all possible wave functions I could emit and absorb from particle 1, emit and absorb from particle 2, or both combinations, then when I add up all combinations of the wave functions, this plus the cross term exactly conspires to give me x21 minus x20 over squared over x21 squared x20 squared, and that's just x1 minus x0 squared over 2 minus 1 squared, 2 minus 0 squared. So when you see the form of the BFKL equation, this integrand is iconic. That's sort of the thing that defines the structure of the BFKL equation. It's a little bit deceptive. This form is the result of adding up those ladder type plus non-ladder type diagrams, and they have different properties. Okay, this equation has all kinds of interesting properties to it. So the first and perhaps most important one is that this evolution equation is not closed. This equation takes something that starts off as a dipole at one scale. And in order to learn how a dipole behaves at this scale, I need to know not only how does a dipole behave at a different scale, I need to know how an even more complicated operator also behaves at a different scale. So if I need to figure out how this operator behaves, now I need to go back to the drawing board and calculate quantum corrections to that operator. And the quantum corrections to the operator for a quark, and a gluon is going to involve even more complicated operators. So let me jump back to the board to maybe sketch this. The problem is obvious, that if I start off with something that had just a single quark-anti-quark scattering, then when I have one quantum correction, now I have a new operator. And if I have two quantum corrections, now I have another new operator. And if I have more, I have another new operator. There is in fact an infinite number of operators, each one containing more and more number of partons that are interacting with the target through these Wilson. So in principle, this contains an infinite number of matrix elements that describe all the many-body physics of many partons scattering in the background field. Another interesting point that's a little bit deceptive about it is that there are regions of phase space of the BFKL equation that look like they actually have two logarithms, not just one. The logarithm that we expect to see is this one that comes from the rapidity variables, the longitudinal variables. But if I go back and look at a subset of these diagrams, for instance, the emissions around particle number 1, all of these wave functions come in with 1 over x2 minus x1 squared. This looks like this integral is trying to become logarithmic. This one, in fact, does become logarithmic if x2 becomes very close to x1. So that phase space, anyway, is becoming logarithmic here. So if x2 minus x1 is very small, then I get a logarithmic enhancement from this phase space that, if the rest of this integrand were order 1, would generate for me not just alpha s log 1 over x, but another log 1 over x potentially. But that doesn't happen because of the structure of this operator. If I go to short distances where that gluon is now sitting basically right on top of the quark, something funny happens to my operator. If x2 is sitting on top of x1, these Wilson lines cancel each other. They stop doing anything. And then I get the same dipole operator, V0, V1 dagger minus V0, V1 dagger. So the first dipole goes away, and then I get complete cancellation of the terms in the integrand. So even though this phase space looks like it's trying to become logarithmic, the rest of the integrand actually goes to 0 in that limit. There's physics in that statement, that even though there's a significant amount of phase space that has the potential to be logarithmic for a lot of interesting short distance fluctuations very close to a single quark, the scattering operator can't tell the difference between them. That's the physics of color transparency, that if I have a quark or a quark with a gluon sitting right on top of it, the S matrix can't tell the difference. Basically, that teeny tiny color fluctuation has infinitesimally low scattering probability, so that if the size in transverse distance goes to 0, the scattering probability goes to 0. And that's what kills off this potential second logarithm here in the ultraviolet at short distance. You can potentially also have logarithmic contributions that come at long distances. Those get canceled for a different reason. Those get canceled because of this, because of competition between the ladder and non-ladder diagrams. That is the physics of color neutrality. That if I have a gluon that is very, very long wavelength, then that long wavelength gluon sees coherently emission from both the quark and the antimatter. And so there, if I add the two together, the total color charge is 0. So there I get screening for a different reason. I get screening in the long distance sector because the total color charge of my dipole is 0. So that's actually a really beautiful feature of the BFKL equation, that this operator is only single logarithmic because of nice simplifications that happen to the scattering operator. That's a very delicate thing, by the way. If you ask a more complicated question like, what if it's polarized? Then you destroy that delicate cancellation and that second log comes back. That's something that I've written various papers on. That's a whole other story of its own. But for the case of the unpolarized sector here, that's why the transverse integrals are actually all convergent. There's no funny business at short distance or long distance, and all of the interesting physics you care about come from the longitudinal log. I keep referring to this as the BFKL equation. That's not strictly true. This is the whole schmear. This is the entire operator hierarchy, which is properly known as the Bolitsky hierarchy of operators. This infinite tower of operators is basically impossible to solve, but you can formulate it in different ways. Another way of writing it is as a functional differential equation, not an ordinary differential equation. That functional version is referred to as the Jim-Walk equation, but it's completely equivalent to this entire operator hierarchy. This contains, in principle, both the physics of high densities and low densities. I haven't made any assumptions about whether my Wilson lines have to be resummed to all orders, or if these Wilson lines have just a single gluon scattering in them. So I should be able to take this general expression and take limits of it to go back to the high density and low density limits. The low density limit is the one where my Wilson line is not very large. So that means in a series expansion that my 1 minus this operator is a small number. So if I take these operators and I expand in 1 minus the trace, I linearize it in that regime, then now by construction, everything is built out of dipoles and I have a closed equation. This is a closed integral equation that you can solve. You solve it essentially by method of Laplace-Mellin transform. And when you find the solution, you solve essentially for the exponent that governs the small x behavior as x goes to 0. And the answer you get from this linear regime, which is known as the BFKL equation, it predicts power law growth of the PDFs, of the gluon density, of the cross-section as a function of x, which is equivalent to exponential growth as a function of rapidity. So in terms of how to think about that, the result of that resummation, I sketched this before. But we said the resummation is effectively supposed to take alpha s times log 1 over x to some power. And if I think of this as an exponential series summing over all n, I expect this to give me exponential of alpha s log 1 over x. And then if I just rearrange the exponential and the log, that would give me 1 over x to an exponent that has alpha s in it. In reality, it's not exactly the exponential series. There'll be some coefficients that show up. Those coefficients will change this number and therefore this number. But the form of the solution from the resummation should be something that has power law behavior in 1 over x, or equivalently, if you prefer in terms of the rapidity y, something which is exponential in the rapidity y. So if you solve the BFKL equation, you actually predict that number. It's this 4 alpha SNC over pi log 2. This number is known as the Pomeroy intercept for historical reasons, dating back to before QCD itself. It's interesting to note that the number that you get from this, if you plug in real values for alpha S and NC, it doesn't agree with the experimental data very well. The exponent that you predict here is sometimes called the hard Pomeroy or the perturbative Pomeroy. The value is much larger than the value that's seen in experimental data describing, let's say, non-perturbative potentially scattering of protons at high energies. So there's some important questions that remain about the role that non-perturbative physics may play at the level of overall hadronic scattering, changing the precise numbers of the intercept. But qualitatively, this should make perfect sense. This is exactly the behavior that we anticipated here, the explosion of the gluon density at small x coming from leading log effects. And that's exactly what comes out of solving the BFKL equation. But the really interesting thing is what happens at high densities. We expect that that exponential growth in rapidity at low densities should turn over and slow down and eventually saturate potentially to a maximum value at high energies. It's difficult to solve the Boltzmann hierarchy identically, but there's a lovely trick that makes it tractable. That trick is a mean field approximation. The mean field approximation can be justified in various ways. One of the easiest ways to see it is by using the large NC limit. In the large NC limit, the color correlations between these multiple dipoles are suppressed. And that's easy to see. If I go back to the board, basically what I want to do to simplify my BFKL equation or my Boltzmann hierarchy is simplify my trace of two dipoles, VC, VW dagger, and approximate it as separate averages of those two traces. VX, VY dagger, VZ, VW dagger. When I'm scattering in the target, some diagrams respect that approximation and some of them don't. So if I have, I don't know, partons in the target and these two dipoles just happen to interact with different ones, then they'll automatically factorize. The times when they don't factorize are when I have one gluon that talks to one dipole and one gluon that talks to the other dipole. That's a communication mediated by scattering in medium. But that is a non-planar diagram. It has gluons going over or under other partons. So that kind of communication is suppressed in the large NC limit. So those correlations are NC suppressed. And so in a large NC limit, my dipoles factorize from each other. They do not communicate to each other through their scattering in the medium. They mostly just scatter on independent gluon fields. And that reduces the full nonlinear equation down to something that you can actually solve. It's nonlinear, but it's all in terms of the dipoles. And this one you can solve. The large NC limit is absolutely perfect for this equation because it is gluon dominated, and the physics we care about is gluon dominated. It captures those nonlinear behaviors, and it's again solved. The qualitative picture that comes out of this is that your gluon distribution in phase space is modified. So on the right-hand side here is a sketch of the perturbative phase space distribution. If you look at the gluon distribution as a function of transverse momentum, here I'm plotting that gluon distribution times KT to soften the infrared behavior. If I have a single quark, that gluon distribution goes like 1 over KT squared. That was what we saw. So the phase space distribution KT times it goes like 1 over KT. So this sort of magenta curve here is the perturbative expectation. You would have a huge number of low momentum gluons that are exploding. The result of multiple scattering due to this high density from all of those Wilson line interactions is that the low momentum gluons get kicked around. Those are exactly the ones that have long wavelengths that are likely to see the medium. And so you decrease the weight of gluons at low momentum and you kick them up to high momentum. This generates a characteristic momentum scale coming from the density. The higher the density, the higher the RMS momentum that you get from a random walk through that dense medium. That is the physics of gluon saturation. The fact that I have random colored gluons that all are giving me random transverse momentum kicks. And just like any random walk problem, as a result of summing up many, many random momentum kicks, you get a typical RMS momentum. The value of that momentum is called the saturation momentum. When you solve the mean field Belitsky-Kopchegov equation, which is this mean field one, then you solve and you can predict how the saturation momentum changes as a function of energy, how it changes with X. The beautiful part about the generation of this potentially hard scale QS is that that dynamically screens the long distance physics. Basically, it's just that if I have randomly generated gluons, the color tends to cancel out if I add a whole bunch of them. And so that means that I only have coherent colors over shorter and shorter distances, the more gluons that I add. So this momentum scale is conjugate to a length scale. That length scale is the correlation length of color fields inside your target. And what the picture is showing here is that the more gluons with random colors that you add in, the shorter and shorter that coherence length gets. That means that there is a perturbative mechanism for turning off long distance interactions at a point that I can choose. That onset happens at a scale controlled by density, the high density of gluons. So if my density of gluons is high enough, I can cut off infrared physics before the non-perturbative stuff kicks in that I don't know how to solve. So in principle, the high energy limit, the high density limit is a perturbative limit because the high density of gluons creates a high momentum scale or a screening effect, a screening length, just coming from the superposition of randomly colored gluons. So I want to close with a message of perspective. Why is saturation essential and what does it solve and what does it not solve? Saturation is inherently related with this question of unitarity. If we do not have saturation, then we do not have a unitary theory of nature. And that's an enormous problem. That is a fundamental problem. So the status quo, the linear evolution scenario, where I try to take the point of view that, well, Hera has seen evidence for leading logs of 1 over x, but they have not seen evidence yet for nonlinear gluon effects. So therefore, we must just have leading log and that's it. We must just have BFKL and that's all. That is not acceptable because BFKL violates unitarity for a reason that's very easy to understand. The gluon density is growing exponentially at a point. So that means if I measure the density in my target, if I have a dipole interaction, even if my dipole is small, even if I'm interacting at a short distance, if I continue to crank up the gluon density, my probability density starts to get too large. And at some point, even in a tiny volume, I exceed 100% scattering probability. That is my indication that this exponential behavior of BFKL is fundamentally broken. So I may know nothing else, but I know that it is not an acceptable theory of nature to have BFKL with no gluon saturation. If you did that, you would violate unitarity because you would literally have scattering cross sections, the scattering probability of your dipole on your target at a point that is greater than 100%. Gluon saturation solves that problem. It solves the little unitarity problem about conserving probability or ensuring that probability is bounded at a point. So what happens instead due to these nonlinear gluon effects is that the growth of the gluon density at the point slows down. Whereas before it just kept on trucking right past 100% and broke, the nonlinear effects change that to an asymptotic limit. So it starts off growing really fast, but then it slows down. And then it slows down more, and then it slows down more, and then only asymptotically over infinite amount of energy and length does it actually converge all the way to 100%, the true black disk limit. So my contention is that saturation is necessary for unitarity. That if I break probability greater than 100% at a point, I have already broken all total probabilities greater than 100%. The thing is that saturation does not solve the big unitarity problem. It does not solve total unitarization of all proton-proton scattering cross sections, and that's where that non-perturbative Pomeron intercept comes in. The issue is that the approach to unitarity at a point is a short distance effect. It's controlled by perturbative short distance physics. The thing that is not controlled by perturbative short distance physics is how fast that black disk region grows in transverse space. There's transverse diffusion of that black disk region as you increase the energy that is sensitive to non-perturbative physics. So to the best of my understanding, saturation is the solution to the little unitarity problem, as I call it. It is not necessarily a solution to the big unitarity problem. Non-perturbative physics is necessary to understand the big unitarity problem. But saturation is absolutely necessary, even if not sufficient, for unitarity. So when I take a step back and I say gluon saturation is great and important and we need to find it for all of the following reasons, yeah, that's true. We want to find an exotic state of matter that has these ultra high density, maybe even maximally high occupation number fields in nature. That's really cool. We want to know about the behavior of a heavy ion at ultra high energies and high densities, partly because that will shed insight on how heavy ion collisions of the quark gluon plasma evolve. That's all true. It allows us to understand something about proton structure from first principles in the high density limit. But to me, it all really comes back at the end of the day to this question about what makes a difference between an abelian field theory and a non-abelian field theory. And at this point, I've laid all of the foundation, all of the arguments to tell you why I think this is so fundamental. Because the simple non-abelian nature of QCD directly, that is exactly responsible for the explosion of gluon density at small x. So if you like QCD because it is a UV complete theory of nature, because it is asymptotically free, because the coupling gets weak and it has all these lovely properties that make it our best candidate for a grand unified theory of nature, the things that make it great also make it terrifying in terms of high energies and high densities. That thing that solves the problem of confinement and asymptotic freedom exactly poses the problem of saturation and unitarization. So it made a huge impression on me when I first heard someone senior in the field like Nestor Armesto say, saturation is non-negotiable. It is a non-negotiable consequence of QCD. It had better be there, or else QCD is broken. It is broken and non-unitary. To me, the question is most prominent if I turn it the other way around. What happens if there is no saturation? What happens if I'm wrong? If I'm wrong and there is no saturation at all, then something is fundamentally broken, not just about QCD, but about all non-abelian gauge theories. This is something fundamental to our ability to understand any candidate UV complete theory of nature. So in my mind, I would argue that discovering gluon saturation, confirming for a fact that it is real and that we understand its properties, is exactly as important as discovering and confirming the existence of the Higgs boson in particle physics. The Higgs was a necessary ingredient for the internal consistency of the standard model. We expected it had to be there. We just didn't know where to look, how high in mass you had to go to find it. But in some ways, as we looked and we looked and we didn't immediately see it, the more interesting question is, what if it's not there? What happens if I destroy the standard model and there is no Higgs boson? That's the challenge that I think confronts us about saturation. We think it is there. We think it must be there, or else the theory is irredeemably broken. But what if I'm wrong? We need to know. Because if this is wrong, everything is wrong. And we go back to the drawing board about fundamental aspects of quantum field theory itself. Okay, so somehow the timing has magically worked out. Thank you everyone very much for your patience, especially with the bit of the rambling last lecture here. I hope the big picture came across. I wanted to share with you why I find this so interesting, why I find it so fundamental, and why I think this is an exciting field for young people to get into, especially with the EIC. Thank you very much. I'm happy to answer questions.
Thank you, Matt, for an absolutely stellar performance every day of the week. That was actually glorious to watch.
Thank you so much for the opportunity.
Do we have some more questions before we have a break? It is really the last chance you have to talk to Matt about this.
For now.
For now.
You can feel free to send me emails, but I'm going to sleep all day tomorrow, most likely. Let me put my email address on the board again if you need it. It is M as in Matthew, Sievert as in the unit of radiation at nmsu.edu, NMSU as in New Mexico State University. Feel free to send me an email. I am not always the most prompt about replying. I'm sorry, but please don't take it personally. It's not that I am not interested in answering questions. Feel free to keep pestering me until I get back to you.
Lots of nodding that you don't see right now. So let's thank Matt once more.
Right. Thank you
He
very much.
really more than earned this. All right, let me stop recording.